Hi guys, welcome to GeeksforGeeks. In this video, we will talk about dynamic programming. But before we start, let's first cover some mathematical background. So consider the following function written on the screen. We have fn equals fn minus 1 plus fn minus 2, where n is greater than or equal to 2. This function gives us a series of numbers called the Fibonacci series. So what's special about the Fibonacci series? Well, what's special is that it has a simple recursive definition. As you can see, the Fibonacci series is defined as a series of numbers in which each number is given by the sum of the two preceding numbers. For example, we get f2 by adding f0 and f1. We get f3 by adding f1 and f2, and so on. Now that we know the recursive definition of Fibonacci numbers, we can easily write a recursive function that helps us calculate the Fibonacci numbers. As you can see, the function fib takes an integer argument n. First, we check whether n is less than or equal to 1. If it is, we return n. But if n is not less than or equal to 1, we recursively call our fib function to calculate the two preceding numbers and we return their sum. Of this property, where a problem has a recursive definition, is called the optimal substructure property. Let's see what happens when we try to calculate fib5. Since 5 is not less than or equal to 1, we first need to calculate fib4 and fib3, and we keep on calling the fib function to calculate the preceding numbers until n is either 1 or 0. The interesting thing to notice here is that we are calling the fib function to calculate the same number multiple times. For example, the right subtree of fib5 is same as the left subtree of fib4, and the right subtree of fib4 is same as the left subtree of fib3. This property is called the overlapping subproblem property. Clearly, we are doing a lot of unnecessary computation. But before we see how to avoid all the unnecessary computation, let's try to figure out the time complexity of the fib function. Look at the recurrence relation written over here. This says the time taken to calculate fib n equals the time taken to calculate fib n minus 1 plus the time taken to calculate fib n minus 2 plus the time taken to add these two numbers together. Clearly, for n less than or equal to 1, t of n is going to be big of 1 because we already know that f1 is 1 and f0 is 0. So we don't need to make any recursive calls. Also, intuitively we can say that tn equals big of 2 raised to n. We can see that from the recursion tree drawn on the left. For n equals 5, we see a binary tree of depth 5. For n equals 4, we see a binary tree of depth 4, and so on. So we see that the complexity of our algorithm grows at an exponential rate. Let's now see how we can avoid all that unnecessary computation. We can do that by storing the results in memory. We can do it in two ways, memoization and tabulation. In memoization, we store the results in the memory whenever we solve a problem for the first time. And next time onwards, we simply do a lookup. While in tabulation, we pre-compute the solutions in a linear fashion and store it in a table to perform lookups later. We will discuss these in more detail in a separate video. And now we are ready to look at the definition of dynamic programming. Dynamic programming is an algorithmic paradigm that solves a given complex problem by breaking it into subproblems and storing the results of subproblems to avoid computing the same results again. Dynamic programming is very much similar to divide and conquer. In both the paradigms, we solve problems by combining solutions of subproblems. However, in divide and conquer, the subproblems do not overlap. While in dynamic programming, the subproblems do overlap, which is why we build a table to avoid unnecessary computations. So now we know when to use dynamic programming. That is, whenever we see that the given problem satisfies the overlapping subproblems property as well as the optimal substructure property. In this video, our focus was on the overlapping subproblems property. In a later video, we will discuss the optimal substructure property in more detail. Here's an exercise for you. Try computing the 40th Fibonacci number on your machine and post the results in the comment section. You might get different numbers, but you will see that both the dynamic programming methods outperform the recursive method. That's all for now, folks.